Okay, I'm going to talk about section 5.3. This is separation of variables, which we actually have already seen a little bit. I did a little separation of variables in the last section because we need separation of variables to get the standard exponential growth and decay equation. It comes from the differential equation where the rate of change is proportional to the dependent variable. So you've already seen this process. So really today, I'm just going to do more examples, and this is going to be our focus. Very algebraic focus. We're not going to be doing slope fields or anything like that. Nothing major as far as concepts, but just sort of plug and chug, good old-fashioned computational algebraic stuff. Okay. Example 1, I want to start off with a problem that technically you don't need separation of variables. First of all, I will give you a differential equation, and it says find the general solution of the differential equation. So sometimes they ask for the differential equation or the solution. They ask you to solve the differential equation. Anytime we give you a differential equation and ask you to solve, you know that means that we're given essentially a derivative equation, and what we want is sort of the original equation. So we're going up the ladder. Now, if your differential equation is exclusively in terms of your independent variable, which you can tell what the independent variable is because that is whatever's in the denominator of the dy over dx. So a lot of times when we're talking about exponentials, it is t. Time is a very common independent variable. In this case, I have x, but just something to look out for because it could be all different things, but it's this to this. So really, in this case, I could just integrate this straight across. However, just to show that this does fall into the separation of variables, I would multiply the dx. There's no y, so I'm just going to have dy by itself, and this will be sine x squared plus x squared, and then dx. So that's actually how I separate multiply by dx, and now integrate both sides. So we're anti-deriving 1, so we're getting y, and that's why we don't actually need to do the separation, because I can just focus on that right side. So this will be negative cosine x plus, and then 1/3 x to the third plus c, and that is what we refer to as the general solution. Okay, so if you're asked to find a general solution, you are finding all the possibilities. That means you're going to have the plus c here. In the past, when we've been turning out integrals, I kind of let it go. If you didn't put the plus c, I'd maybe mark it, but I wouldn't take off points. In this context, leaving out the plus c is going to cost us quite a lot because a lot of times we have to use that c for something else. So make sure you're on top of that. Okay, so that is the end of example 1. I'm going to move on here, and we're just going to be kind of going through examples today. Okay, for the rest of the examples, we are finding particular solutions. So I will typically find a general solution first, and then at that point, we'll be plugging in the initial condition to solve for y, thus finding the solution that's particular to that point. So once again, if it has a plus c, that means we have all the possible solutions, the general solution, and then once we plug in this point, that is when we get the one and only one solution that goes through that particular point. Okay, so let's take a look at this. We're going to separate variables, so we're going to get the y stuff over here, get the x stuff over here. So what I get is dy over y squared is equal to 3x dx. Now, once we get these things like this, it's only multiplication and division. We don't want to use adding, subtracting, unless I'm moving some things, which we'll see down the line. Now I'm going to integrate both sides. Now let's be very, very cautious here, because a lot of times at this point people will start calling this ln of y squared. The only time we get an ln is if it's degree 1 in the denominator. Don't lose focus on how we integrate these things. So we're going to call this y to the negative second dy. So then when I integrate it, I get negative y to the negative first. So that's my integral on the left. Now, we don't need a plus c on the left, as I showed in the previous video, because it just sort of morphs into the other one. We only need 1 plus c. Since ultimately we want to solve for y, we really want that plus c on the other side. So the antiderivative of this side is 3/2 x squared plus c. Okay? So now it's time to solve for y. And I will tell you that on the AP test, it's pretty common we have to solve for y. Technically, that is a general solution, but they usually ask for the form y equals f of x. So I'll tell you that my approach is I always say solve for y first. So solving for y, the first thing I'm going to do is multiply both sides by negative. Y to the negative first, I'm just going to call that 1 over y. So this is going to give me negative 3/2 x squared. There's no point in calling this minus c. We just call it plus c. Basically, anything we multiply, add, or subtract directly to y, we're going to leave, anything we add, multiply, or subtract directly to c, the arbitrary constant, we'll leave c until we plug that point in. Once we plug that point in, that c is sort of locked in place, but up until then it sort of has this morphing quality. However, it does have to follow the mechanical rules of algebra. So for instance, here I'm going to flip to get y. So I get y is equal to 1 over negative 3/2 x squared plus c. Notice that c has to go to the denominator. It can't be outside of that because this whole thing is to end up in the denominator. So that is one of those things that people sometimes have difficulty with. They'll have this right here and then they'll have the plus c outside of that. So c has this quality that if you multiply things directly to it or add or subtract or whatever, it just sort of absorbs it, becomes c, but it does have to follow the mechanical rules. Now this is our general solution. So at this point we're going to plug in whatever initial condition they gave us. So 1/4 for y. I would say explicitly show this. Negative 3/2. By the way, I could simplify this. I could multiply by 2, or I can leave it, which I'm going to leave it. So then we're plugging in 2 squared plus c. All right. So now at this point, what I realize is that the denominators have to equal because the numerators are equal. So I get 4 is equal to. If you wanted to cross multiply, you could see the same thing. Whatever gets you there is fine by me. So 2 squared is 4. 2's cancel. That's 2. So this is negative 6 plus c. So what that means is I get c is equal to 10. Now some people will make the mistake of thinking that that is our solution. That is not our solution. A solution to a differential equation is always the y equals thing. So I'm going to get y equals, and now I want to put it all together. 1 over negative 3/2 x squared plus 10, and this is my particular solution. Now if you did simplify it, like if I look at a multiple choice, they would probably multiply top and bottom by 2, but that's not necessary. Okay, I'm going to leave it like that. Let's move on to example. Okay, example 3, this one looks a little different. Remember y prime, that's just dy over dx, which is maybe how I want to rewrite this. Now here's the deal, before I can even start the separation of variables process, I need to get that ln of x on the other side. So I want to rewrite this thing as 2x dy over dx is equal to, and then ln of x. So, as I talked about, once we start separating the variables, we want to only use multiplication division. That's when we're splitting up this rate of change. To just move that ln of x or that minus ln of x on the other side by adding it is perfectly fine. Now at this point, once we get this thing the way we want it, we want to move things according to just using multiplication and division. Now this one actually ends up being, so let's just move this around. I'm going to get dy here. There's no other y's, so that's going to be by itself on this left side. And then over here, I'm going to get ln of x divided by 2x, and then I'm multiplying by dx. So at this point, I actually don't have to think about this because the integral of this will be 1, that's y. So from here, I'm only integrating the left side. However, I do want to bring out this 1/2. It's just going to be easier for me. And then the ln of x, keep in mind that we won't need a u sub to deal with this. This is not a typical u sub, because usually with u subs, I tell you to let u equal whatever the composite function is. Here there is no composite function. However, we do not know the integral of ln of x. That is something that we cannot do until we get to the next course. So in this class, whenever you see ln of x, it really has to be something where that is going to be the thing you let equal u. So what we're looking for is the fact that if I let u equal ln of x, the derivative of that is 1 over x dx. So now I'm getting a match for this. Okay, so I get y is equal to 1/2, and then ln of x is going to be u du. So it's not the typical u sub. But as I was saying, really in this class, until we get to the next level, the only way we can integrate something that involves an ln of x is if we let u equal ln of x. Okay, so let's take the antiderivative. So y equals 1/2. You have u to the second, and what I realize is I need a 1/2 to cancel with that. So I have 1/2 times 1/2, so we'll call that 1/4. And then let's go ahead and plug in the ln. So this will be ln squared x. By the way, this is similar notation you've seen with sine and cosine. You could put this in parentheses to the squared. What you don't want to do is just have this because it looks like we're just squaring the x. So you could put the parentheses, or you can do what I did there. Now once again, this is the general solution, but we want the solution particular to that point. So now we're plugging this in. 2 equals 1/4, okay? ln of 1 plus c. Now, ln of 1, keep in mind, this is asking a question, what do I raise e to get 1? Well, I'm going to raise e to 0 to get 1. So this is just 0. So what we get here is c equals 2. So now we put it all together. So this is our general solution. Our solution particular to the point is y equals 1/4 ln squared x plus 2. And that is my particular solution. All right. Okay, this problem, once again, I want to do a little simplifying before I go separate variables. Realize that cosine in the denominator is actually secant. So this one, it's a good idea to do a little rearranging first. So I'm going to call this dy over dx. So I'm not separating yet, but I'm going to call this secant squared x over y. Because once again, keep in mind that cosine in the denominator, 1 over cosine x is actually equals secant x. So I can bring this out, think of it as secant x, and then I get secant squared x. So now I'm going to go ahead and separate. So I get y dy is equal to secant squared x dx. And this is where I say you've got to know your derivatives literally forward and back, because as secant squared x, you should recognize the antiderivative of that is tangent of x plus c. So really keep reacquainting yourself with those derivatives. We've got to know those very well if we're going to go forward with them, but also remember to go backwards when we integrate. And this is going to be 1/2 y squared. Once again, we only need the plus c on this side. Now let's solve for y, okay? So I'm going to multiply everything by 2. So I get y squared is equal to 2 tangent of x plus c, all right? And now I'm going to take the square root. Don't forget, when we take the square root, we do need a plus or minus. Now this gets a little tricky, and here's the thing. In the general solution, we want the plus or minus. However, what we're going to be talking about when we're finding solutions is these solutions are always going to be asked in the form of a function. This is not a function. So it's not really a plus and minus, it's a plus or minus. It depends on the point. So you look at the point here, because the output of this, so let's plug this in, -9 equals plus or minus, and then 2 tangent of pi over 4 plus c, okay? We're either going to accept the positive or the negative depending on the value, the output we have over here at y. So we know that in order, because the square root is going to be positive here, it has to be positive. You can't even plug anything negative into it. So if this is negative over here, we have to be accepting the negative. If it was positive over here, we'd only accept the positive, okay? So the plus or minus in the general solution is fine, because it's going to depend on what the initial condition is. However, for the actual particular solution, it depends on whatever this value is here. So since it's a negative, we're going to accept the negative. If this was a positive 9, we would accept the positive. Okay, so from here, multiply both sides by -1, we get 9 is equal to the square root of. Tangent of pi over 4 is 1, so this is 2 plus c, okay? So then let's square both sides. So we get 81 is equal to 2 plus c. So solve for c, we get c is equal to 79. Once again, that is not the solution. Our solution is to put it back together. Keep in mind, we're either going to accept the negative or the positive. So here we're accepting a negative to ensure we're getting out that -9. And this will be 2 tangent x plus 79. and that is my solution that is particular to the point. All right, we have one more example, and that's going to be it. Like I said today, very much plug and chug algebra. Okay, last example. Let's just go ahead and start. Hopefully you've got enough repetitions that you're starting to see these patterns here. So we're going to separate the variables, divide the y on either side. So we get dy over y equals 6x squared dx. So now that I have those separated, I'll integrate both sides. Now we're going to get the ln. So on our first example or second example, it was one of the earlier examples, we had y squared in the denominator. And the way I deal with y squared is I call it y to the negative second raised to the power. If you mistakenly do it this way, so if you think, oh, I'm going to call that y to the negative first, you have to remember when I raise that to power, I get y to the 0, which then we deal with that logical issue that y to the 0 power is 1. How can that be the antiderivative when we know the antiderivative of 1 is 0? So just remember when we have that degree 1 in the denominator, it's ln, and we do want the absolute value of y. Okay, you need the absolute value here, otherwise the domains won't match. The domain of this is the same as that. Without the absolute value, the domains of those don't match. Okay, we're raising this a power. We have a 6 there, so I'll leave that 2. And you know, at this point, it's a good idea to practice your integration by differentiating. Okay, now we have to solve for y, which means I want to write this in exponential form. So keep in mind, ln is log base e. So I'm going to rewrite this as the absolute value of y is equal to e to the 2x, e to the 2x to the third plus c. Now, the absolute value of y, we also saw this with the exponential ones, and this is going to have some similar mechanics. I will tell you a lot of this becomes repetitive and you don't have to show it each time. However, I'm going to show it at least one more time here because it is just so peculiar. But anyways, let's start off with the absolute value of y. If I have the absolute value of x equals 8, I know that x is equal to negative plus or minus 8. So as soon as I see that y over here, I can call this plus or minus. Okay, so then I have e to the 2x to the third. Now, when I see e to the something, you know, call it a plus b, realize I can rewrite that as e to the a times e to the b. And like I said, this is the mechanics that we saw in the last one. That's one of our exponential rules, is that when we have like bases and we multiply, we add the exponents. So I'm going to do the opposite. I'm going to multiply these. So this, realize, is the same because if I put it together, I would add those exponents. Okay, hopefully that doesn't seem too strange to you. Now, that is a general solution, but we want this in this nice form, realizing that plus or minus, if I call this y equals plus or minus e to the c, and then e to the 2x to the third. So all I did was move that e to the c to the front. Keep in mind, multiplication is commutative and associative, which means I can move the factors around however I want. This thing is just, once again, an arbitrary constant. The only thing that can't represent is 0, and if this thing's 0, the whole thing sort of blows up anyways. So we're just going to rename this y equals c e to the 2, y is equal c e to the 2x to the third. All right. So this is our general solution here. What I'll tell you is, once we see this enough, you know, if you go skipping from like, you know, these steps in here, that's perfectly fine. So now I'm going to plug in this point. So e to the fourth is equal to c e to, and then 1 to the third. So 1 to the third is just 1. So this is e to the fourth is equal to c e squared. And now to solve for c, I'm going to divide both sides by e squared. E to the fourth divided by e squared, now I'm subtracting exponents. So 4 minus 2, that'll give us e squared is equal to c. And now let's put it all together. So y equals e squared times e to the 2x to the third. That is a perfectly good solution. However, a lot of times when you have these like bases like this, what they're going to do is they're going to combine that and then add those exponents. So I am, like I said, perfectly fine with this. However, in a multiple choice setting, it's likely that they'll simplify this down to this. So what I'm doing, once again, is the opposite of what I did here, right? So I have like basis, so I'm adding those exponents. So whatever form you leave it in is fine by me. It really doesn't make a difference. Okay, so that is my solution particular to that point. So this is what we're going to be practicing. This is one of those things, it seems quite unfamiliar and quite strange at first, but with some practice, we tend to get quite good at these things. So that's 5.3, separation of variables.